Hello again. It is I, Mrs. Fisher. This is our last set of notes for this gigantic unit. I know you're sad. But today we are going to be discussing Unit 7, Day 8, Parametric Curves. So we talked last video about making parametric lines, and we did do some with circles. This is going to be talking about parabolas. So, kind of the idea of going straight and curving at the same time almost. So, parabolas. Lines and circles should have been kind of straightforward because we were using, lines basically just make a table. In the circles, we were using the same formulas that we used throughout this unit. Parabolas is where it goes off the rails a little bit. So here we have to do a little bit of thinking. So a couple pieces that we need to kind of put together. So for parabolas, this is where we are going to be thinking about objects being launched through the sky. So something being thrown in the air, something being shot through the air. But what goes up must come down. And if you think about it, anytime we've talked about this in a previous math class, we've only been talking about either height with respect to time or horizontal distance with respect to time. But really all of these objects have all three of those components. They have horizontal distance, height, and time that come into play in terms of where this object is actually going. So a parametric equation is really the best way to describe what's going on. So in order to really understand what's going on with this, you need to consider this whole thing in terms of a vector that represents the velocity at which this object is first leaving its initial spot. So we are going to be talking about a vector for initial velocity. So that's really important. And in order to talk about that vector, we are going to have to use the components that make up that vector. So we need the x component and the y component of that vector. So that's one thing we're going to need. We're going to need the vector. The other thing we are going to need to talk about is we're going to need to talk about how distance, so where this object is going to equal rate times time. So like how far we drive in our car is going to equal how fast we're going times how long we have been driving. Okay, so those two things put together is going to be how we come up with our parametric equations. Okay, so let's talk about the first one. The horizontal distance, the x, is going to be found by doing distance equals rate times time. Now, our rate is going to come from our vector right here. So when we talk about that, we're going to talk about the velocity, our rate, in terms of just the x. We're only talking about the x part. So our x part is going to be the magnitude of our vector, so that's the velocity, and then cosine of the angle at which this object is being launched at. So I'm going to go back up there and put a little theta. So that is the x component of our vector. So initial velocity times the cosine of the angle, that's the x component of the vector, so that's our rate, and then times time. So our distance that we're going horizontally is our rate times time. Okay? Now y, we're going to do the same idea, distance equals rate times time. So we're going to have a y component. I'm going to leave some space, do our y component. Distance equals our rate in the y direction. So that's our rate. So the y component of our vector times time. But there's a lot more to what's going on vertically. So the other parts of our vertical component have to do with how high off the ground our object was starting to begin with. Because a lot of times if something's being thrown in the air, you're not throwing from zero. You're throwing from wherever your arm is, or if you're launching something in the air, it's not quite at zero. So at the end here, I'm going to say plus initial height. And then down here, I'm going to say h equals initial height. Okay. And in the front of this equation, there's usually a component that is for gravity, because gravity is what makes your object come back to the ground. So there's also a gravity factor. Now this gravity factor can take two forms, depending on if your height is being measured in feet or if your height is being measured in meters. Okay, so if your height is being measured in feet, this is a negative 16t squared. So this is for height being measured in feet. So this is for feet. If this is being measured in meters, then this would be a negative 4.9. All right, so we've got your x component and then a y for feet and then a y for meters. And yes, you need to memorize these. Okay, so everything that I'm highlighting, you do need to memorize. We are going to practice with them in class. You need to have those equations memorized. Okay, so I'm first going to ask you to write equations Okay, so I'm going to have Kevin. He's going to hit a baseball at 3 feet above the ground with an initial velocity of 150 feet per second at an angle of 20 degrees. Okay, all I want us to do today, right now, is write parametric equations. Okay, we can actually solve some cool problems with this. Like talk about if he hits a home run or not, things like that, but that's all done in the calculator, so we'll talk about that in class. So to set up parametric equations, we would first talk about what's going on here. He's hitting, okay, he's hitting starting 3 feet off the ground, okay. The angle at which he's hitting this at is 20 degrees, right? And then the initial velocity, so this little vector right here, that force at which he's hitting this is 150 feet per second. Okay, so the x component of the vector is 150 cosine 20. That's the x component of the vector. So again, the distance that this ball is going to go is going to be that rate, the x component of that rate, times time. So we're just going to do that times time. So that's your x equation. The y equation is going to be gravity. So that's, we're in feet, so negative 16 t squared. And the squared part is what makes this curve like a parabola, plus the y component of our velocity. So the y component of our vector is 150 sine 20. So that's the rate times time, plus how high this ball was off the ground to begin with, which is 3. So those are your equations to model this situation. Okay, so if you feel comfortable graphing that in the calculator and want to check it out, you can do that, but we will talk more about how to do that in class, since a lot of it's in class. So that's all for today, friends. To make up for the long one last time, we are finished. So peace out, Boy Scouts and Girl Scouts. Hope you've enjoyed this unit as much as I've enjoyed it. We'll catch you on the flip side.